Hello everyone, this is Gürtaç Yemişçioğlu. I would like to give you a brief overview of my research. I divided my presentation into three parts: the main motivation of our research, the past research, adiabatic logic and logarithmic signal processor, and current and future research, quantum cellular automata. Beyond CMOS techniques, so our main motivation. So why beyond CMOS techniques? The relentless miniaturization of integrated circuit technology over the past 50 years has resulted in ever-increasing circuit densities. For the most of this time, the main motivation of miniaturization has been to increase the computational performance by building faster and more powerful processors. As Moore's law stated, and the graph shown over here, the number of transistors in an integrated circuit will double roughly every 18 to 24 months. So we are shrinking down the transistors and we are putting more transistors in an integrated circuit. The die size grows by 14% to satisfy Moore's law. As we are shrinking down the transistors, we are actually approaching the atomic levels, the limits of CMOS devices. So if we are reaching to these atomic levels, we are actually feature sizes shrinking 30% every 2 to 3 years. However, in recent years, these advances have resulted some desirable side effects, which we can talk about, like complexity. So how do you know it will serve intended purpose? Like power density. How do you dissipate heat at such small space? Like robustness and reliability, soft errors, timing errors, defects, variations, and circuit unreliability and reduced battery lifetime because of increased power consumption. And also, another consequence of technology scaling is leakage power. Now, continuing trends towards high performance and portable computing and communication devices have exacerbated these effects, and now minimizing power consumption, it actually becomes one of the major challenges in the design of modern electronic systems. And this is our motivation. As a result of this, there's an increasing interest in the application of low power computing techniques at the system, architectural, algorithmic, and circuit levels. In this research, which I have done in the past, adiabatic logic logarithmic signal processor, um, my main motivation, as I stated in the Beyond CMOS techniques, I have implemented power reduction techniques at algorithmic level, architectural, and circuit level. So I would like to describe that briefly. Now, the circuit shown here is an adiabatic logic. It's a circuit topology which we use in ultra low power devices. It's a quite new technology. It's powered by the PCK, which is a power clock. It's a dual rail. So if you have in, you will have in prime as well, which is inverted input, and out prime. So this is a typical buffer design where we have got buffer and inverter implemented at the same circuitry. So what's the idea behind this adiabatic logic? Rather than using DC voltage and charging and discharging the capacitors and dissipating all the energy as heat to the ground, we are actually slowly charging the capacitors, and we are slowly recovering that energy and holding inside of the circuitry. So rather than dissipating all as a heat, we are just dissipating small amount as a heat. And based on this circuit topology, I have implemented a logarithmic signal processor. Now, you might ask, why logarithms? So, because multiplication and division in the linear domain is performed as an addition and subtraction in the log domain. So, multiplication and division in linear domain, it requires extensive calculations and logic devices. So rather than using those, we can just use others and perform those operations in log domain. This is why hybrid logarithmic processors are attractive alternative nowadays. In order to implement logarithmic processors efficiently, we need algorithms. to convert the linear number to logarithm and logarithmic numbers to linear. And in our research, we have used Mitchell algorithm, which is one of the most used and easy to implement in VLSI design. So what we are trying to do over here, if we can prove that, we can use the architecture, algorithm, and adiabatic logic together, we can actually achieve ultra low power devices so that then we can use this approach and implement more accurate, more comprehensive algorithms using this approach. Um, I can show you the architecture insights where we have got the lin to log converter, log to lin converter based on the Mitchell algorithm and the arithmetic logic unit. If you need more information, you can contact me to get more information related to this. If I carry on, this is the chip that we have fabricated, which we have used AMS 0.35 micron process technology and fabricated. The areas are also important because our aim was ultra low power and compact device that we can use in DSP algorithms like hearing aids and so on. Now, as a result, this is the board that I have designed so that we can locate the chip just the center of the board, which will be connected directly to an FPGA development board Nexus, so that we can monitor the outputs from the logic analyzer. So FPGA used over there to fire the inputs to the board. And as a result, as you can see from the digital outputs of the logic analyzer, we can achieve that PCK, which is a power clock and the auxiliary clocks, and we supply some random data inputs like 2 and 3 and multiply that to obtain 6, and we can easily observe that throughout our actual device. So this was actually confirmed, the simulations that we have performed, which is the verification of the device is working. Now, one of the important things, as I mentioned in the beyond CMOS techniques, is the power consumption. So what we have done is we have compared our adiabatic logic implementation, the simulation, and the actual device versus the CMOS implementation. And the red the graph is showing actually the CMOS implementation, which is quite significantly much energy dissipation compared to our implementation. So the power measurements have showed that the clock adiabatic based implementation energy efficiencies increases linearly up to 89.5% as the frequency increases up to 100 megahertz when compared to the equivalent conventional CMOS implementation over the entire range of the frequencies tested. And we believe that these power reduction techniques together will have a great impact on DSP applications where the performance and the accuracy are inversely proportional to the power consumption. Now, as a result of this implementation, high precision, high performance, and ultra low power logarithmic signal processors are possible. And you can find the publications related to this research over here. Okay, next is our current and future research, which is based on quantum dot cellular automata. Now, as I mentioned in the Beyond CMOS techniques, the microelectronic scaling is approaching its limits, ultimately arise from fundamental laws of statistical mechanics and thermodynamics. This is why it is becoming increasingly urgent to investigate and implement alternative circuit techniques or designs, the materials, or maybe a computing paradigms that can enable the continuation of this exponential growth in computing power that we will increasingly rely on for advancements in almost all industries. As a result of this, there's an increasing interest in the application of low power, high density, fast switching speed, and room temperature operations, as I mentioned. Now, quantum cellular automata is one of the promising future solutions because QCA is emerging technology that takes the advantage of quantum effects, which they become increasingly apparent at the scale of few nanometers. And QCA is based on encoding of binary information in the charge configuration within quantum dot cells. as you can see the figure over here. So the two black electrons, as you can see are on the opposite corners, represent binary 1 polarization on the left, and when they are changed, polarized in the other way around, they are binary 0, which is polarization -1. Now, the local interconnection between cells are provided by the physics of cell-to-cell interaction due to arrangement of electron positions, like in the wire over here. And as a result of this, QCA can be used to create smaller electronic devices with very high computational switching, low power consumption. Therefore, QCA becomes popular and important to replace CMOS transistors in nanoscale technology fabrication. And you can see a QCA wire, which can be used as an interconnect, number of cells next to each other. QCA inverter is just two diagonal cells, actually can be represent as an inverter. And in order to represent any logical function, majority gates can be used, where if you want to represent two input functions, you just need to fix one of those inputs to either 1 or 0. Now, another important thing in QCA is the clocking, because clocking in QCA, clock provides both power and the clock to the circuitry, and efficient clocking needs to be implemented. And this is generally based on adiabatic switching, where one clock cycle has 4 phases. And each has its own characteristics, like switch phase. Cells can be polarized, hold. The polarization of the cell cannot change as the barriers are raised, and release barriers are lowered, so the cells can be depolarized, and relax. The cells still depolarized, but can be repolarized to another logic level. And we can easily demonstrate that in a time step, as shown on the bottom with the number of cells along the wire. So as you can see, each of these are in a different color codings, which represents the different zones. So for example, if we start from the left white cell, which is polarized to logic 1, and if you look at the right white cells, which they are polarized to logic 0. Now, logic 1 is going to polarize the cells on the right, but in the clock zone 3, where we have got the white cells on the right, they're in the hold phase. So they're keeping the state of those cells as 0. Now, if we start from left and go up to the right, which is like a wave, so in clock zone 0, it's the switch phase. So as we have got in the white one is 1, the dark greens are going to be 1. And the purple ones, they're in clock zone 1, they're in relaxed phase. They are waiting for to be polarized in the next phase. And clock zone 2 is in the release phase. It's going to be in relaxed in the next, and the hold is going to be releasing the next. So when you change the time step, as you can see, the dark greens are going to polarize now the clock zone 1, which is in the switch phase, and the dark greens are in the hold phase. So it's holding over there so that they can polarize clock zone 1. And the other two clock zone, where zone 2 and zone 3, one of them is in the relax, other one is release. So they don't have polarization anymore. And in time step 2, as you can see, the cells on the left, the dark greens and the whites, they are just depolarized now, so release and relax states. And the purple and the light green ones, one of them is holding, so the other one can be polarized in the switch phase. And the clock zone 3 is in the relax phase, waiting for to be polarized. And the time step 3, this is happening. So this is how QCA is working. The methodology is over here, and you can implement any type of logic functions using these wires and the majority gates. So me and my team, we are currently concentrated on two areas in QCA. One of them is optimization of 5-variable functions using majority and AOI gates to implement QCA logic blocks with reduced area, latency, and reduced depth. So we are trying to optimize it so that we can implement more complicated functions. And our second motivation or focus is on the implementation of optimized logic functions for AI accelerators. Now, AI accelerators are quite popular at the moment for artificial intelligence implementations and algorithms, and we really need AI accelerators which are fast and ultra low power. And we believe that by applying QCA techniques to these logical blocks, it's going to give us some promising solutions for future developments. So that's all I want to say. And my team at the moment, Embonel Mijema Godwin and Ahmed Mamdouh, they're both MSc students at this university. We are currently working on these two topics. You can get more information from me or from them. And if you would like to contact me, please do not hesitate to contact. That's all I want to say. Thank you. Have a good day.